This video is on buffering capacity. Buffering capacity refers to the amount of acid and base that you could add to a buffered solution until you start seeing a significant change in pH. So we're going to look at two. They're the same general buffer solution. We're just changing the molarity. They are indeed buffered solutions. We've got acetic acid, a weak acid, and its conjugate base, the acetate ion. In both cases, sodium is really just a spectator. We just need some kind of a soluble acetate salt. Let's first figure out the pH of the original solution. I'm assuming that we may prefer the Henderson-Hasselbalch shortcut. You could do an ice table if you really wanted to, but I'm going to use the shortcut if that's all right with you. So here we go. You can leave water in, you could leave water out. The general equation, we would have the weak acid, hydrogen acetate, 3O2. If you wanted to put the water in, that's just fine. And then this guy's going to dissociate. We're going to have the acetate ion, O2. And then you'd either have hydrogen or you would have hydronium, H3O. Either's fine. I'm not going to set up a full ice table. I'm just going to look at the concentrations that I have. And maybe we can kind of tag team this. Let's call solution A, like I'll do solution A in red. And maybe we can do solution B in purple. And then we can kind of do this at the same time. Solution A is 5 molar acetic acid. We're not going to care about the water in either situation. And we're adding some of the acetate ion, 5 molar. Initially, we have 0 of the hydrogen or hydronium ion. And we're going to have something similar with the second solution. Molarities are just a little different. So it'll be 0.05 molar. We don't care about the water. And then this too will be 0.05 molar. And the hydrogen or hydronium is 0. So we can set this up. We can use the Henderson-Hasselbalch shortcut if you would like. Solution A. pH equals opposite log of the Ka value, 1.8 times 10 to the negative fifth. That's a weird looking 5. That's a 5. There we go. That's better. Plus the log. It's always the conjugate over the neutral particle. And in this case, we don't really care because they're both 5 molar. 5 molar. And then I can do the same setup for solution B. Our concentrations are just a little bit different. You might see where this is going. Opposite log of the same Kb plus the log of, what do you know, 0.05 over 0.05. In both cases, you're going to get the same pH. The initial pH, is approximately 4.74. That might be something that we'll want to reference in a minute. The conjugate acid base buffer solution doesn't have to be the same molarity, like, the conjugate acid and the base, or the base and the conjugate acid. In this case, they are. Often they are, but they don't have to. It's kind of nice when they are because you just get the log of 1. So we've got the same initial pH, 4.74. Now let's do a little BS. Let's do a little buffer stoichiometry. We are adding, what do we got? 0.01 moles of gaseous HCl to a liter of each solution. Okay. So here we go. If we're adding the HCl, I want to start with definitely the hydrogen ion as a reactant. And if you wanted to, you could kind of think, well, here's all the particles in the solution. You've got your buffer. It's got the weak acid, O2. Then you've got the sodium ions. You've got the acetate ions. O2. We're adding HCl, which is going to be hydrogen and chlorine ions. And there's always water. We can always list water. Hopefully we would recognize the sodium and the chlorine are spectators. Coming from strong acid, strong base, they have zero effect on the overall hydrogen concentration or the pH. But I definitely need hydrogen on the reactant side. And again, I think sometimes that's where people get stuck. They just don't know what kind of a reaction to write. Well, it's got to be something plus hydrogen. And then I ask myself, of the particles in the buffer, which one can react with hydrogen? And then I'd say, oh, well, it's that base, H3O2. That's the one that can pick up the hydrogen. Let's give myself a little more room on that. Plus hydrogen. If I do that, I should form the weak acid, hydrogen acetate. 3O2. So again, it's a trade-off. Instead of having extra free-floating hydrogen ions that would have a strong effect on the pH, we're going to trade that in for a little bit of weak acid, some of that acetic acid. Okay, so let's do this ice table. ICE. And again, maybe we can kind of tag team this as we go. I think I did solution A in red. Initially, solution A was 5 molar. And we are adding, was it 0.01? Yep. 0.01 moles of hydrogen per liter. So we can just call that molar. And this was 5 molar. We did have some of that acetic acid in the original buffer. All right, so the idea of a buffer is that we're going to react this as completely as possible. We want to get rid of all that strong acid hydrogen. So hopefully I can react this down to 0. At equilibrium, the strong acid's gone. And then everybody else reacts accordingly. This will go down by 0.01. So at equilibrium, I'll be looking at 4.99 molar. The products are going to go up by 0.01. At equilibrium, I'll be 5.01 molar. All right. I got my new molarities. Now I just got to find the pH of this resulting solution. It's probably easiest to use the Henderson-Hasselbalch, right? Opposite log of the Ka, 10 to the negative fifth, plus the log. Ooh, it's not 1 anymore. The conjugate over the neutral particle. 4.99 is my conjugate base. Over 5.01, my weak acid. I plug this in my calculator. We had been leaving about, I don't know, maybe like 2 decimal spots or so. I might take this out a little bit and say 4.738. That's for solution A. The pH barely changed. The original buffer was 4.74. If I would have left that at 2 decimal spots, I wouldn't have even noticed a change. That's why I just wanted to leave a little bit more precision at the end there, so we can see that there is a change. We added some strong acid hydrogen. The pH dropped slightly, ever so slightly. Let's do the same thing with the other solution now. It'll be real similar. Okay, same equation. Acetate ion can pick up the extra hydrogen, forming the weak acid. 2H3O2. All right, we ice table. And now we plug in our original concentrations. This time they were smaller, 0.05. I don't know why that's only 1 sig fig, but it is. The hydrogen's the same, 0.01 or 0.010, I guess. And then this guy's 0.05. So again, I'm going to try to react this as completely as possible. In a sense, it's kind of like the hydrogen's my limiting reactant. I'm going to get rid of the hydrogen, so at equilibrium, it's gone. That's down to 0. Everybody else reacts accordingly. We're going to go down by 0.01 moles. This is going to be 0.04. This guy's going up by 0.01. At equilibrium, we are 0.06. All right, let's do the new pH. Opposite log. The Ka value, 1.8 times 10 to the negative 5th, plus the log. Ooh, these are different. The conjugate, 0.04 over the neutral particle. Ooh. So plug that in my calculator. I get a little bit more of a change this time, 4.56 for solution B. I mean, it's still not bad. If we were to add this acid to water, we would see a significant drop in pH. But this time the pH changed a little bit more with solution B. And you can probably kind of guess why now. When we talk about buffering capacity, we're looking at but how much hydrogen or hydroxide can we add until the hydrogen or hydroxide becomes my excess reactant. You can't add any more hydrogen or hydroxide than what you have to start with when I look at the molarity of the original buffered solution. So the more concentrated the buffer, the greater the buffering capacity. I can add more hydrogen or more hydroxide. These are both good buffers. But that 5 molar buffer is better. It's got a better buffering capacity. Say that 10 times, hanging upside down or something like that. So if they ever asked you something along these lines, we should maybe make a little note up here. These are both buffered solutions. They've got the weak acid. They've got the conjugate base. A better buffer is going to have larger molarities or greater concentrations. Larger concentrations. There's just a greater buffering capacity then. I can take more hydrogen or more hydroxide without seeing a significant change in the pH.